All right. Well, can you guys hear me? Okay. So today, yeah. Well, thanks for the introduction. But yeah. So today I'll be presenting on zkSpeed, an accelerator for zero-knowledge proofs. We focus on HyperPlonk, which is a recent state-of-the-art protocol that presents many desirable properties for wide-scale deployments, but incurs high computational costs. zkSpeed is the first ASIC to accelerate HyperPlonk, and we do this with a heterogeneous SoC that tailors individual blocks to the disparate needs of various computational phases. We perform a comprehensive design space exploration to build full chip architectures for a range of performance targets, achieving 801x geomean speedups over the CPU baseline for our headline result. So to start off, how do zkPs work? So consider an example where Alice wants to see a movie with the age minimum. Now in this case, she would have to prove that she's of age to see this movie to Bob, who might be a ticket collector. The way she would normally do this is she would give her ID to Bob, and then Bob would check that she's of age. But the problem with this approach is that while Alice proves she's old enough, Bob learns everything about Alice by looking at her ID. This is not necessarily desirable. What if Alice does not want to disclose her age? What she can do is she can use a zero-knowledge proof, or a zkP, to prove to Bob that she's old enough without Bob learning anything about her or her age. So this is the crux of zkPs, where a prover essentially convinces a verifier that they know some sort of information without revealing anything else. This involves a computation such as a function f with two inputs, a public input and a secret input, matching an expected output y. The prover will run a proving algorithm on these two inputs to generate a proof, send the proof to the verifier, and the verifier will verify the proof with the public input to see if it matches with the expected output. It never uses the secret witness. So in a zkP protocol, we want to ensure that an honest prover is always correct, a malicious prover fails to cheat, and a verifier learns nothing about the secret witness. So zkPs have a ton of applications that are promising in these days. So for one, in electronic voting, a person can use a zkP to prove that they legally casted a ballot without revealing who they voted for. Cloud-based ML applications can certify they use a specific model without revealing the model weights. And in private transactions like on the blockchain, a sender can confirm and prove that they made a legal transaction without revealing the transaction amount. And just a few months ago, Google just announced that they're starting to use zkPs for private age verification. So we are at the cusp of seeing zkPs being deployed. But this begs the question, why aren't zkPs seen everywhere? And the reason for this is that zkPs are slow. So why are zkPs slow? It boils down to the inputs and the computation. So zkPs operate on long polynomial vectors that are very wide, and they have expensive modular arithmetic computation on elliptical curves under the hood. This leads to zkPs incurring a slowdown of roughly 100,000x compared to the original computation being proven. So to address this, we present zkSpeed. In zkSpeed, we accelerate the HyperPlonk protocol, which is gaining traction in the zkP world because it offers universal setups and small proofs. Small proofs in particular are important for zkPs because we want to use zkPs in consensus-based systems where a single prover convinces multiple verifiers of the validity of their computation. There's two key kernels in HyperPlonk that we accelerate. We accelerate some checks and MSMs as well as the full protocol. And through our efforts, we achieve orders of magnitude speed up on the individual kernels and the overall protocol. To quickly explain why some checks and MSMs matter, some checks are used for checking polynomials that represent the integrity of the computation, and then multiscalar multiplications, or MSMs, are used to verify the witness confidentiality is being maintained. These two kernels account for roughly 93% of a total proving process, but in zkSpeed, we accelerate everything. So as a roadmap, I'll be talking about some checks, MSMs, and the HyperPlonk protocol in this specific order. So let's start with what some check is. So in some check, we're trying to make a claim about a polynomial that the sum of all the binary evaluations of that polynomial is some number h. This seems kind of complicated, so let me simplify it. Polynomials actually map to lookup tables in hardware. So you might have a lookup table that looks like this, and all we're really saying is that the sum of all these evaluations, h, is 24. Does this mean we can just sum up the table? Unfortunately, the answer is no. This is because in SumCheck, we have to engage in a multiple round protocol for where each round is responsible for making a claim about one variable in the polynomial. So there's 3 variables in this example, so we run 3 different rounds of this protocol. Today, I would just be talking about one round of this protocol, but please note that the rest of the rounds follow recursively. So in the first round of SumCheck, what we're essentially doing is we're going to make a claim about the variable x1 by summing over the variables x2 and x3. A key assumption in HyperPlonk is that the function f is multilinear, which means it is linear in all of its variables. That means that when we sum over the variables x2 and x3, the resulting polynomial itself is linear. That means that we can uniquely characterize it with 2 evaluations along its line. So the question now remains, how do we find these evaluations, and do they meet the claim, which is their summation adds up to h? The way we do this is we just take the table, find which values of the function have x1 equal to 0, add them up. Then we look for the values where x1 is 1 and add those up. And then we can add them together to verify that the claim was met. After this point, we want to proceed to the second round of SumCheck, which involves eliminating this first variable by fixing its value to a random number. This effectively reduces the size of the table by half, and then we can proceed to the next round. So thus far, this seems pretty straightforward. You're just accumulating values and updating a table. So the challenge with HyperPlonk is that in HyperPlonk, we have polynomials that are a little bit more complicated. For example, you might be multiplying 3 polynomials together. To reconcile this, what ends up happening is when you sum over those remaining variables, f1 of the first variable is actually a degree 3 polynomial, and to uniquely characterize this, we need 4 evaluations. So how does this work? What does the data flow look like? So I'll first explain the first polynomial as an example. You might have a table that looks like this. What we're going to do is we're going to iterate over different values of x3 and x2. So we'll start at 0, 0, and we want to construct the evaluations at 0 to 3. First, we perform a table lookup to generate the first 2 values, and then we extrapolate the values from those first 2 values. We repeat this for the next instance of x3 and x2, and so on and so forth, after which point we have to accumulate these values vertically to get the polynomial evaluations for the first function, g1. We now do this for the remaining tables, and then we compute the product across these tables to get the ultimate evaluations. And lastly, we have to update these tables before we proceed to the next round. So all of this seems a bit complicated. So what are the architectural insights that we can use to cut through all of this math? So for one, within a table, there's immediate reuse, and there's parallelism within the table. Then there's parallelism across tables and across the evaluations. And lastly, we'll note that there's no long-term reuse of these tables. So how does this affect the microarchitecture for zkSpeed SumCheck? So we can think of an example again, G, H, and M. First, we can partition these tables into equal-sized chunks and allocate each of these partitions to an individual processing element, leveraging intra-table parallelism. Then, if we look inside a single PE, what we can do is reading these tables in parallel, leveraging inter-table parallelism, extrapolating the evaluations, leveraging inter-table reuse, and then computing the products in parallel, leveraging evaluation level parallelism. Putting this all together, we remember that there's no long-term reuse of these tables, so we can just stream them from off-chip memory without using expensive SRAMs to store intermediate tables. So again, this was an example for a simple polynomial, g times h times m. In HyperPlonk, we're actually dealing with much more complicated polynomials, but it turns out that the same architectural insights extend to these more complex polynomials. So now I'll talk about MSMs in brief. I'll note that due to time, I won't go into too many details, but there has been a large body of literature that currently exists. So MSMs are essentially dot products on elliptical curves. What we're dealing with are 2 vector sets, a set of wide-word scalars that come from the polynomials, and a set of wide-word 3-dimensional points on elliptical curves that come from the proving key. The challenge here is that these multiplications are point multiplications, which are expensive because point multiplications are actually repeated point additions, and then a single point addition is very expensive. This is a visualization of what a point addition might look like. To quantify the cost, we consider the fact that a single MSM might involve 2 to the 20 or a million point multiplications. A single point multiplication requires 2 to the 256 point additions because these are 256-bit scalars. And then a single point addition is 16 modular multiplications, meaning in total that's on the order of 2 to the 280 modular multiplications. This is an insane computational cost, and there has to be a way to reduce it. So what prior works have done is that they've looked at Pippinger's algorithm, which is a way to essentially partition the computation into parallel bit slices of these scalars called windows. And this significantly reduces the number of point additions that are needed. And on top of that, within a window, you can group point additions together to significantly reduce the compute burden. The challenge is that in prior ASICs, there's been three main challenges. For one, there's very high area overheads for storing these points needed to support dynamic control logic to keep your pipelines fully fed. And on top of that, there's a lot of data-dependent behavior, which limits the scalability because of parallel memory contention during parallel memory accesses. As a consequence, it's very hard to scale these existing ASICs. In zkSpeed's MSM, we use our prior work from SCKP, which address every one of these challenges with area-efficient address storage, simplified work scheduling logic, and contention-free memory accesses, which makes things easy to scale in our algorithm. Additionally, we reduce memory footprints in zkSpeed, as well as speed up some computations, and we achieve roughly 1300x speed up over the CPU's MSMs. So now I'll quickly talk about the HyperPlonk protocol. So HyperPlonk's protocol involves four main steps that must be executed in series. At a high level, this involves basically MSMs and sum checks. So this is what the actual data flow looks like. This is very, very complicated, and it poses many challenges. Namely, different kernels have different constraints. Some are memory bound, some are compute bound. Different kernels also have different compute patterns. And lastly, because we want to accelerate the full protocol, by Amdahl's law, we must accelerate everything. So to this end, we propose a heterogeneous SoC with custom modules integrated with a shared bus, HBM, and global SRAM. Due to time, I won't go into too many details, but I will point you guys to the paper to look at our novel modular inverse unit and a novel tree unit. To better understand how the data flow maps under architecture, I'll give an example of a simplified version of the wire identity. So the wire identity step involves three main steps. The first step involves constructing a bunch of tables. So it starts out as the SHA unit communicating with the NND unit over the shared bus. Then we read some tables from the SRAM into the NND unit over the shared bus. Then the NND unit writes tables to HBM and the fraction unit over the shared bus and the HBM. The fraction unit writes results to the product unit over the shared bus, and the MSM unit over the shared bus, and then out to HBM as well. And lastly, the product unit writes tables to HBM. This is just the first phase. The second phase involves continuing the computation of MSMs, which involve reads primarily from HBM, and there's two of them. After this point, the MSM communicates with the SHA unit over the shared bus, and this imposes a serialization bottleneck based on the order of operations in the protocol. In the third phase, we compute sum check, which is first initialized over the shared bus with SHA, and then we engage in the multiple round protocol, which involves transfers between the HBM and these core modules, as well as transfers over the shared bus with the SHA unit. So our approach to this is to overlap as much computation as possible. And because we pipeline units together, we can effectively eliminate the first step's latency from the critical path. That being said, there is a protocol level bottleneck, which means we do have to serialize some of these computations. So mapping this entire data flow is clearly a very complicated endeavor because there are many things that have to be balanced. Resource allocation, memory bandwidths. So to this end, we construct a full chip design space exploration using cycle accurate simulations and performance models. In our design space exploration, one question that comes out is, do we really need high bandwidth memory? So to better understand this, what we can do is we construct these Pareto frontiers for different architectures in our design space at different memory bandwidths. And we compare for a problem size of, in this case, 2 to the 20, which is roughly a million length vector sets. The CPU baseline takes 8,600 milliseconds to run. So in this case, if we want to hit 100x speed up over the CPU, we can do just fine with 120 gigabytes per second of off-chip bandwidth. But if we want to get to 1,000x speed up, we really do need to invest in higher memory technologies. And the reason for this is in our architecture, because we made the sum check streaming, the sum checks are now memory bound. So we can add as much compute as we want, but until and unless the memory bandwidth is not satisfied, we get only marginal returns. For our comparison that we highlight, we pick a design that's roughly ISO CPU area. And in this design, we add higher memory technologies. We use, for example, 2 terabytes per second of HBM bandwidth. And this incentivizes higher resource allocation to the sum-check units. And this allows us to improve the performance another 7.8x over 100x target. So to better understand or better visualize how this area comes into play, we can look at the global Pareto frontiers in this design space. And what we find is that as we allocate more and more memory bandwidth, the resource allocation percentage given towards sum-check grows. It's initially skewed towards MSMs, which are compute bound. But as we scale up, we see more and more areas going into the sum-check units, which are in the blue in the pie charts. So in sum, our framework enables us to construct a variety of chips, meeting a wide range of performance targets under varying compute and memory constraints. So in sum, this is zkSpeed, the first ASIC to accelerate the HyperPlonk protocol. We developed scalable modules, in particular the sum-check and MSM, to construct full chip architectures, achieving an 801x geomean speedup over the baseline CPU implementation. Thank you, and I'm happy to take any questions.